to answer. But anyways, we have a really exciting lineup of speakers for you today. However, before we get to the speakers, as always, we have a few announcements from the division for you. So as some of you may be aware, the ACS Fall is coming up quickly. It's taking place in Chicago. So that's August 24th to August 27th. And the division, as well as our glorious program chairs, have been really working hard to prepare some really great symposia and award talks for you. So if you are able to attend, I highly recommend you check out at least some of these incredible lectures. In addition, the Graduate Research Symposium is quickly upcoming, so that's taking place in about a week at Emory University from July 23rd to 26th. And if you're fortunate to attend, there's a really great lineup of speakers there as well, as depicted on the slide. Lastly, the Amos Smith Award, which is a new award from the division, is calling for nominations. So the deadline for nominations is September 15th. The awardee will be presenting at the NOS, taking place at the University of Minnesota in July of 2027. So if you know of anyone who meets the criteria, please submit a nomination. The link is provided at the bottom of the page, as well as through a convenient QR code. So we're looking forward to the nominations. And on that note, I am very excited to introduce our first speaker, Erin Stash, who's an associate professor at Princeton, who will, as you will come to find out, has had a very interesting journey getting to where she is now. So as I found out reading her website, which was very informative, by the way, Erin, prior to coming to Princeton, Erin conducted graduate work at Colorado State University. But being unsure of whether she wanted to pursue academia or industry, Erin left and worked for a year at a local pharma company. Following this, she moved to California and worked in a laboratory focused on materials engineering for aerospace and automotive applications. So, pretty diverse scope of work there. This experience ultimately convinced her to return to academia and finish her PhD. After her PhD, Erin conducted her postdoctoral work with Professor Brett Fors as one of the inaugural presidential postdoctoral fellows at Cornell. Today, Erin's research group is focused on advancements in efficient synthesis and polymer utilization. Thank you for dedicating your time today, Erin, and presenting at this forum. We're really looking forward to your presentation.
Thank you so much for that kind introduction. Surprised, I didn't even know I had all that on my website. No.
Yeah, it's very helpful. So,
all right. Share screen. Here we go. You can see my slides.
Looks perfect.
All right, great. Well, thank you so much to the organizing committee for inviting me to give this seminar. I haven't given a talk in a really long time, so I'm a little bit nervous. But I'm really excited to tell you what we've been working on throughout my independent career for about the last 6 years. I changed my title, so I'm going to talk about photothermal conversion and how it's applied to organic synthesis. And so photothermal conversion is sort of exactly what it sounds like. It's converting those photons of visible light into energy, thermal energy that you can then use to drive chemical reactions. And so very simply, you imagine irradiating particles or dyes that can undergo photothermal conversion. They'll take that light energy, convert it into heat, and then near the surface of that particle or dye, it's going to be very hot, and that heat will diffuse away into lower temperatures as it moves away from the surface. So there's been a number of research works done in this area, Ben Lear, Laura Clark, and many others who have sort of pioneered some of the early work, specifically identifying photothermal conversion particles. And if we can think about photothermal conversion as compared to conventional organic heating, when you run a thermal reaction, right, you program in a temperature, and then it'll go at a certain rate constant based on the temperature and the thermodynamics of the reaction. The photothermal conversion is somewhat unique in that only near the surface of the particle where you have sufficient energy to drive a chemical reaction. And so you'll have a very large rate constant near the surface, and this will diffuse away as you move away from the particle. So this should allow you to achieve spatial and temporal control over the reaction and achieve much cleaner product distributions as opposed to just bulk heating. If you think about how this is working, you can increase the population of your reactive species such you can now overcome the barriers for uncatalyzed reactions. Typically, we use catalysis. We're trying to actually overcome some of these barriers, not using catalysis, just using this introduction of photothermal heating. But there is some reactivity considerations that we have to take into account. Specifically, when you have this local phenomenon, you need to have your reactive species near the surface of the particle in order to take advantage of that thermal energy. And so if you're thinking about intramolecular versus intermolecular reactions, you have very different reactivity principles you need to consider. And I'm going to talk about these through each of my different stories today and how we think about using photothermal conversion from anywhere from polymer synthesis, depolymerization to small molecule organic reactions. So first I'm going to talk about polymer chemistry, then eventually I'll end on some synthetic chemistry, synthetic organic chemistry. So polymer architectures, advanced polymer architectures are all achieved through controlled radical polymerizations. And these are really important for a number of applications, anywhere from viscosity modifiers to a lot of biomedical applications. We like to have good control over the polymer so we can take on these different properties and make these different materials. And so one way to achieve controlled radical polymerization is through atom transfer, right? So you're just transferring a deactivating group off of your polymer chain so you can control the radical concentration and avoid side reactions like radical-radical coupling. And so you can do this with a number of different metals. We're specifically interested in cobalt. So you take a cobalt-2 metal with an alkyl halide. This will reduce the alkyl halide to generate a propagating radical, which can then make polymer, and then a cobalt-3 dormant species. And then you control this equilibrium by the cobalt catalyst and the alkyl halide that you're using so that you have more of these dormant species rather than having a high radical concentration. So you control this dissociative exchange of the halogen. And so this can look like a catalytic cycle. Cobalt-2 activates the polymer chain, you generate your propagating radical, and then cobalt-3 can regenerate the dormant state. Now, there are some other considerations, like I mentioned, terminations. If you have too high of a radical concentration, you'll get to these dead polymer chains and you'll build up cobalt-3 concentration. So you need to find a way to convert cobalt-3 back into cobalt-2. And so when we started in this area, we were looking at vitamin B12 derivatives as a potential way to use biocatalysts to control radical polymerizations. And so we came up with this HME Cobb catalyst. And when we reduce this from cobalt-3 to cobalt-2, this can reduce the polymer chain to generate our propagating radical. And as I showed before, this propagates with vinyl monomers and generate your polymer chains and close the catalytic cycle by oxidizing your chain and reinstalling that bromide. And so there's a small thermal barrier for this activation event. We run this reaction at about 60 degrees C. We found that we could use a variety of different alkyl halides as the initiator, and we could use very low cobalt catalyst loadings, which is good because vitamin B12 is not the cheapest catalyst. But in thinking about making advanced polymer architectures, one area of research to consider is photocontrolled polymerizations. So you can get spatial and temporal control over your three-dimensional architecture. And photoredox catalysis has been used before to activate these polymer chains, use a highly reducing photocatalyst in its excited state, and you can generate your propagating radical and then recap the polymer chain, just like I showed you before. And so we thought that with this cobalt catalyst, having this Corin core, having been used in other types of photoredox processes before, we thought that maybe this would engage in a photocontrolled radical polymerization. And so when we turned on the light and used white light LEDs, we found a very well-controlled polymerization, converting about 50% of the monomer, low dispersities, and good initiation efficiencies, suggesting that our initiator is starting one polymer chain. And notably, in the dark, we don't see any polymerization, a very low conversion of the monomer. But when we turned to our colleagues to understand the photophysics of this process, Dan Oblinsky ran some transient absorption for us. And what he found is a metal to ligand charge transfer event, unexpected, but which was surprising, is that there was a very rapid back electron transfer, so 4.6 picoseconds, which is not long enough to engage in bimolecular chemistry. And when we add in alkyl halide and run the same experiment, we see the same excitation. We also see a very rapid back electron transfer, slightly longer, but still not sufficient for doing that excited state reduction. And we observe no excited state quenching of the alkyl halide with the cobalt complex. So we propose that this is actually undergoing photothermal conversion. So rather than excited state chemistry, in the dark or at room temperature, we have a cold catalyst. It's very slow activation. We don't see polymerization. But when we turn on the light, now we're generating these thermal gradients as the heat is released from the catalyst. And this will result in fast activation. So we can promote our polymerization with good control and rapid polymerization. So it's a photo-controlled activation, but it's through a thermal process. So we can still get that spatial temporal control that you love from photo-controlled polymerizations, but it is still a ground state thermal reaction. More evidence that this is a photothermal process. We doped in larger concentrations of the cobalt catalyst in the absence of monomer, and we do see a temperature increase when the light is on. So there's a background increase of about 2 degrees, but as we add in more and more cobalt catalyst, you generate more heat, and the reaction mixture warms up. So you can see some IR camera here. At the beginning of the reaction, it's a little bit cold here in Frick, about 20 degrees C, and then after some period of radiation, you can see that the vial has warmed up when it has a cobalt catalyst. And we compared this to a standard iridium catalyst like iridium PPY, which we would typically use for a photo ATRP process, and you don't see any bulk temperature increase here. And that's because it's undergoing photoluminescence, it's giving off light, it's not giving off heat like our cobalt complex is. And when we really blast it with photons, you can see we can actually boil the solution. The cobalt catalyst is generating enough heat that it's boiling the monomer. This is not active polymerization. This is just showing that the catalyst is getting hot. We showed that this will work with a number of different wavelengths, so anywhere from broad spectrum white LEDs, UV to red. You see pretty similar end polymerization results, although the kinetics are a little bit different. So if anybody's curious, we can talk about that a little bit more. We can use very low catalyst loading, so down to 0.2 mol%, and pretty good still control over the polymerization. And most excitingly, we show that we have temporal control. So polymerization only occurs when the light is on, we turn it off, polymerization stops, so on and so forth. And where this is really important and how to contrast this is through the thermal polymerization. So when we first developed this chemistry, we used AIBN to introduce a few radicals into the system. And so you have to run that reaction at elevated temperatures. And so you can turn off the heat, but that doesn't stop the polymerization because the bulk temperature is high. And so the polymerization continues to proceed slowly until the bulk temperature gets low enough that it will shut down. This is in contrast to our photothermal process where you see the polymerization stops immediately when the light is turned off. And that's because the bulk temperature is very low. It's only warm near the catalyst surface. And regardless, in both systems, we achieve very good control over the polymerization. So thinking about this from photothermal conversion perspective, how do we interpret these results? We're running this reaction in solution. So you might think that the catalyst will generate this heat, but that most of that heat would be lost to the solvent, and you wouldn't actually see productive chemistry. And so what we think, especially when you're running these reactions in solution, you need to have a very good association between your substrate and your photothermal catalyst, in this case, the cobalt. And so what we think with the transient absorption spectroscopy data, when you see that longer excited state lifetime in the presence of the alkyl halide, we believe that's because it's associating to the cobalt catalyst, such that when it's hot and it's able to activate the alkyl halide, it is in proximity, and you get very efficient thermal transport and electron transfer. And in a different system where you use a thiolate ligand, you can actually see a shift in the UV-Vis absorption spectrum when you add in alkyl bromide, suggesting that there is this pre-association of the initiator to the cobalt complex. Okay, so that's the polymerization that I was going to talk about. I'm going to move on to a lot of the work that we do in depolymerization. So I'm sure you all are well aware of the plastics crisis that we're facing. And so many of us have put a lot of effort into converting the carbon content that's lost in plastic waste back into useful products, sometimes other commercial products, but very commonly trying to chemically recycle it back into the monomers so you can continue to make virgin polymers. And so the reason this is so challenging for most of our commercial polymers is that the polymerization is very enthalpically driven. You're going typically from a vinyl polymer into a long chain alkyl backbone. And so all those polymerizations run downhill. And so in order to reverse that process, you need to put in a lot of energy. So for polystyrene, for example, if we think about polymerization at room temperature, we start up here and we end up way down here when we make the polymer. But of course, there is an entropic penalty for stringing all of these monomers together. Now, at a certain temperature, called the sealing temperature, the rate of polymerization and depolymerization becomes equal. So you have equal populations of these species. So if you want to drive depolymerization, you want to make the monomers more stable, you need to get well above the sealing temperature so that KEQ is much less than 1. You can drive depolymerization, recover those monomers, and then make more polymer. You can imagine for vinyl polymers, this number is very large. So there's a huge energy input. For polystyrene, the degradation temperature, so that's to break the carbon-carbon bonds in the backbone, is about 350 degrees C. And then the sealing temperature for polystyrene is about 400 degrees C. So that's a temperature you need to achieve to induce depolymerization back into the monomer. So for context, polystyrene pyrolysis, when it's done commercially, is typically done about 500 degrees C to get efficient depolymerization. You still get a mixture of co-products as well for degradation. So we need to break the carbon-carbon bonds in a very efficient manner, and we need to maintain these high temperatures for depropagation and try and avoid all of the side reactions. And so we thought photothermal conversion would be an ideal strategy for inducing depolymerization. And so carbon black is a very common photothermal agent. It's been used in a number of different applications, and it's incredibly cheap. And notably, it's used a lot in the plastics industry. So if you think about all the black plastics that are out there, most of these are going to be formulated with some type of carbon black. It's a very efficient photothermal converter. It's essentially a black body. All of that light gets turned into heat. And so we thought this might be an interesting strategy for trying to depolymerize these commercial plastics. Interestingly, black plastic recycling is nearly zero because it can't be sorted very efficiently until recently. And so all of this material ends up in the landfill. And so this work was all carried out by Seiwan, Hanning, and started by Liat. And what we wanted to have a very controlled system. And so what we started doing is synthesizing polystyrene with carbon black incorporated. So we actually used carbon black in the synthesis. So we made these polymer composites, and then we exposed them to white light irradiation under vacuum distillation so that we could recover the styrene monomer and quantify these other byproducts. And so what we found is that without any carbon black, you don't see anything. The light is not enough to activate the polymer backbone. And as you start to increase the carbon black loading, you see pretty efficient depolymerization, almost 60% yield of the styrene monomer. Dimer and trimer are very common byproducts from depolymerization. You can see a fair amount of those, and then a small amount of leftover polystyrene. And here's just a video to show you how this depolymerization works. We just have the vial of black powder sitting above the light, and then you will see very quickly, as the light is turned on, we generate those thermal gradients. It breaks those carbon-carbon bonds, generates monomer, and all of that moisture coming up is the monomer being pulled off. So it's very fast and very efficient. And as I mentioned before, carbon black is used extensively in the plastics industry, up to 40%, sometimes in composites, even higher. And so we found these 8 different polystyrene containing products. They're not all pure polystyrene. They have other materials, fillers, and other polymers in them, but all of them contain what is likely carbon black. All of them contain some polystyrene. And we did not add anything to these samples. All we did is cut them up into smaller pieces, put them in the vial, and shine the light. And we're able to recover the monomer using the formulation that is already in these products in very comparable yields to somewhat more modest yields. So we're very excited that we could just directly depolymerize plastic waste and recover the monomers. Now, of course, we're still plugging into the grid, right, using electricity to power our LEDs. And so we question whether or not we could use sunlight, which is obviously our most renewable resource. And so if we focus the sunlight using a Fresnel lens, with pure polystyrene, we don't see any depolymerization. But when we do this with the black polystyrene foam, in just 5 minutes, we see 80% yield. You can see this is much higher than even the yield we can get with the LEDs. I think this is because of the higher solar intensity, we're getting much hotter and therefore depolymerizing at a much higher efficiency. Now, the nice thing about this approach is that you don't need to have the carbon black directly incorporated into your plastic. You can take a mixture of black plastic and non-black plastic and still get depolymerization of the entire species. And that's because the carbon black isn't being consumed, right? It's just getting hot, it depolymerizes everything around it, and then as it comes into contact with this clear plastic, it's able to depolymerize that. So even at 25 weight% of black plastic and 75 weight% of clear plastic, we still get over 40% yield with our LEDs, and with sunlight, we're well over 60%. And we can take a whole mixture of different polystyrene products that we can get off the street or after we use the materials, and we can get up to 70% yield using sunlight. So this is a different situation in how we're thinking about photothermal conversion. Instead of running a reaction in solution, now we have a solid state reaction. So we have our polymer mixed in with carbon black. Because it's a low mobility polymer, it's high molecular weight, it can't diffuse away from the carbon black even when it gets hot. And so that heat is efficiently transferred to the polymer, breaks those carbon-carbon bonds, and then it generates monomers, which are high vapor pressure, which are moved away from the surface of the carbon black, so we don't see repolymerization. And so photothermal conversion is ideally suited for depolymerization of commercial plastics. But of course, there's still some issues here. How do we incorporate the carbon black into the polymer? Sure, some polymers have black plastic, but others you have to incorporate the carbon black in some other way. The surface area of irradiation, I often get questions about scale up. Pretty challenging in this system to get an efficient scale up. And of course, if you're using carbon black, you're going to have this build up over time, even if it comes in the black plastics. And so we teamed up with a colleague here at Princeton, Professor Craig Arnold in Mechanical and Aerospace Engineering, and they were looking at porous carbon materials derived from egg white for a number of different applications, but one of them was for filtering polystyrene microplastics, which was pretty successful. And so we hypothesized that this carbon is likely photothermally active, and we could depolymerize microplastics or potentially even more commercial plastics. And so the idea now is that you would have this highly porous carbon material. The polymer would sit on the surface, and as the carbon is irradiated, the polymer will melt and infuse into the pores and then induce depolymerization. And the monomer could either come out the side the polymer is going in, or if you could develop a flow setup, it could come out the other side. And so now you have a very high surface area of photothermal material. You have a reusable scaffold, and you can imagine scaling this in some type of flow setup. All this work was carried out by Dr. Jang. So this is some photographs of the carbon material. You can see after 1 minute of irradiation, the polystyrene that was sitting on top is now sort of melted and infusing into the pores after 3 minutes. And then after 10 minutes and 20 minutes, most of the polymer is gone. Some SEM images also show this. The polymer is sitting on the surface, and then after longer reaction times, the polymer is depolymerized and we can recover all the monomer. We can also reuse this scaffold up to 5 times without any loss of efficiency. Nice thing about this system and photothermal conversion in general is that it's very polymer promiscuous. It can work with a number of different materials. So polystyrene, 64% yield, MMA, and then we can also perform ring closing depolymerizations, so polycarbonates or polylactide in high yields. PET, we can add an ethylene glycol, and now we can depolymerize this and recover 96% yield of this potential monomer. Again, this works on commercial samples. It's very important for us to try our chemistry on commercial materials. And so with styrofoam or other different polystyrene containing products, we get very high yields. And in this case, all we have to do is put the plastic on top of the carbon, we irradiate, and it all depolymerizes. Works with plexiglass, a number of different PLA samples. This one is kind of interesting, this plastic bag. So it says PLA on it, but if you actually take an NMR and analyze it, it's like less than 20% PLA. It's other probably polyesters. So when the plastics say it's a certain polymer, all it means is it contains a little bit of that polymer. It does not mean that it is actually primarily composed of that. So good to know. And then PET, a number of different plastics. So water bottles, we can even take some of our lab trash, so NMR solvent containers and depolymerize that. And then polycarbonates also work really well. And here's another video to show how simple and easy this process is. You can see down here, this is the porous carbon, and this is just a little chunk of styrofoam in the vial. You turn on the light, and the styrofoam just sort of melts into the carbon, and then you can see the vapor rising as the monomer is generated. Let me go back to that. And so in this, I'm not going to show you the scale up, but we were able to scale this process up to 10 grams, much more efficiently than we could with pure carbon black. And we use, I think, about a tenth the amount of egg white by mass as we do in carbon blacks. This process is very exciting for potential scale up applications. Okay, so moving on to some small molecule chemistry. Carbon black or photothermal conversion is not unique to polymer applications, polymerization or depolymerization. You can also imagine using this for high activation barrier reactions. And so we applied this to the Newman-Court transformation, classic reaction converting phenols into thiophenols through a unimolecular rearrangement. And so we take our starting material, we mix it with carbon black, so you get this little powder. We irradiate it for up to 40 minutes, just set it on top of the light, and you get your product in nearly quantitative yields, and all you have to do is filter off the carbon black at the end. And so this is a very simple, efficient way to run a reaction at about 300 degrees C. Instead of using an oil bath or a sand bath, we just have this powder and irradiate with light for a few minutes. Very rapid conversions across the whole gamut of substitutions here. We can do very electron-rich and very sterically hindered Newman-Court substrates, and we can choose the product distribution depending on the wavelength of light or the intensity of light that we use. And I'll talk a little bit about that in a future reaction here in a second. So this work was all carried out by, I got to update the slide, it's now Dr. Megan Matter, one of my former PhD students. Of course, the Newman-Court was a great demonstration, but we wanted to move on to more challenging, like bimolecular reactions. And so, of course, CN bond formation is very important for pharmaceutical applications and agrochemicals, found in all these top 200 selling drugs, of course. Typically, this is done through transition metal catalysis, Buchwald-Hartwig coupling. longer reaction times, expensive ligands, higher temperatures, etc. And so we wondered if we could use photothermal conversion to forge these carbon-nitrogen bonds in the absence of transition metals, and using photothermal conversion so we can achieve this under ambient atmosphere and in very rapid timeframes. This work was carried out by Megan, Rory, and Christina. And so we thought we could achieve this through an SNAR reaction. Classic reaction, typically a two-step process. Nucleophile adds in, form this Meisenheimer intermediate, and then elimination of the fluoride will give you the coupled product. Of course, this is usually restricted to aryl fluorides and very electron withdrawing substitutions, so typically nitros or multiple nitro groups. Now, more recently, a concerted SNAR has been probed computationally and experimentally, where instead of going through the Meisenheimer intermediate, you go through this very high transition state energy species, and where you're making and breaking the bonds in one step, and you get to your desired product. So it's a concerted pathway, and it expands the scope of electrophiles to chlorides and bromides, and you can use more electron donating substitution, which of course would expand our plethora of CN bond forming reactions. And so we started out with this bromotrifluoromethylbenzene, typically not used in SNAR reactions. The CF3 is not activating enough, and it's thought to go through a concerted pathway, using piperidine as a nucleophile, DBU as a base, use red light, mild intensity, and some carbon blacks. This is a heterogeneous solventless reaction, and we can achieve the coupled product in 28% yield in just 2 hours of irradiation. Now, for context, if you want to run this reaction thermally to achieve a comparable yield, it takes about 180 degrees C in an oil bath. And if we want to get to near 100% conversion or yields, we can run this reaction for extended time periods. Now, we often get questions on how do you think about light intensity and temperature? And we're still working on this. We don't have a full answer yet, but here's just a plot of light intensity versus reaction yields for this particular reaction. You can see with lower intensities, this is a shorter time frame, you don't see any yield, but as you increase the light intensity, you're increasing the temperature at the surface of the carbon black, and so you get a higher yield, you get more productive reactivity. Now, if we try a more challenging intermolecular reaction, so if we go with this 3-bromopyridine, now we basically don't see any reaction. We get very low yields, even with extended reaction times. We can increase the intensity, so if we nearly double the intensity, we do start to get some yield in just 30 minutes, but we see a lot of dehalogenation of the pyridine, and so we don't get productive chemistry. And so this was interesting to us, and so we wanted to look at this computationally, and you can just look at the activation barriers, and they're very different, right? This is a more activated substrate versus this 3-bromopyridine, and so maybe this can be explained just by the difference in activation barrier. But if you do the computations, that doesn't actually pan out. And so we wanted to find a comparable activation barrier, but with an intramolecular substrate. So we tethered this amine to this bromobenzene using similar reaction conditions. Now we can get productive chemistry in just 5 minutes. We get 33% yield of the intramolecular reaction, even though we have a similar activation barrier. And so this gets to the point of intermolecular chemistry and using photothermal conversion. So as you get closer to the photothermal agent, the probability of colocalization is going to be very, very low. And so for an intramolecular reaction, this doesn't really matter. You'll get enough stochastic interactions with a photothermal agent. As you get close enough, you can promote the reaction, and there's no problem. But the intermolecular chemistry, as you get very close to the photothermal agent, you're going to have zero probability of seeing a productive reaction because the entropic penalty for bringing those two things together at such a hot temperature is near zero. So you have this sort of sweet spot in the distance of the photothermal agent where you can actually do productive intermolecular chemistry with these high activation barriers. And so this is one of the challenges we're facing in promoting this chemistry. So one way to overcome this challenge is to do a sequential SNAR process where we first do an easier SNAR that can occur further away from the photothermal agent, and then a second SNAR into the less activated position. And so if we have this diamine with this halogenated pyridine, we first couple at the less activated, or the more activated position, the 2 position, and then a second SNAR into the less activated position, now from an intramolecular substrate, gives us a desired product in high yield. We get excellent chemoselectivity, of course, for the more activated substrate, and we only see reactivity at the 3-chloro position because of this intramolecular nature of the reaction. These types of sort of interesting heterocycles, they map on well to different pharmaceutical agents. And we can do this with a number of different nucleophiles. We can do pyrazines, which are much more activated. Um, we can use other types of diamines. We can also use um, sulfur nucleophiles or a mixed nitrogen sulfur nucleophile to make larger rings. And we can even do this quadruple SNAR reaction in modest yield. We sort of get to all these interesting heterocycles using this method. But of course, this doesn't really overcome the problem. How do we access these high barrier bimolecular reactions when we have this challenge of trying to co-localize our reagents near the photothermal agent when it's hot enough? And so the way we overcame this in the stories that I've shown you so far, one, we basically had an intersphere electron transfer from our cobalt catalyst to our alkyl halide such that we could promote polymerization. And so when the catalyst gets hot, when it's irradiated, the halide is in proximity to receive that electron, and then that can go on and react to make the polymer away from the photothermal agent. Polymerization, we have the solid state polymer, and that's near the surface, and so that can easily depolymerize. What we really need to have is substrate proximity to our photothermal agent through some sort of non-covalent interaction or a transient covalent interaction. So how can we have our two bimolecular substrates come into contact with the photothermal agent when it's irradiated so we can have productive chemistry? And so one way we're demonstrating this is through a decarboxylative ketonization reaction. And so we take two carboxylic acids with our catalyst. This is unpublished, so I don't have the catalyst on here, red light, and we generate this intermediate, and through decarboxylation, we get to the desired ketone. This is all work that's been done by a rising third-year graduate student, Amory. This is actually a pretty old reaction. So ketonization has been around for a long time. So we used to make acetic acid or acetone from acetic acid. Typically, in industrial processes, this will occur well over 400 degrees C, but at least over 300. A lot of gas phase chemistry, very poor cross selectivity. You can imagine there's an opportunity here to make non-symmetric ketones, and it uses a lot of designer catalysts. And so in this case, what Amory's been able to show is that we can take a number of aryl carboxylic acids with this alkyl carboxylic acid in just 1.3 equivalents, so not in a major excess. We use our charred catalyst, and we get to our cross-coupled product in very high cross-selectivity. You can see here, yields are often very high with different substitution. We can tolerate heterocycles, both furan and thiofuran. And what's sort of interesting here is one of the byproducts we'll see in these lower yielding reactions is decarboxylation. So the carboxylic acid, the aryl carboxylic acid is decarboxylated near the surface of the catalyst. And we're able to overcome that by going in with the ester instead. And so we have very slow hydrolysis over time to generate the carboxylic acid. And so we use a more bulky ester, we can actually improve that yield from nothing up to almost 50%. This works for other types of heterocycles where decarboxylation is more prominent and very electron-rich substrates as well. And so we're continuing to work on this. We can make a in situ ester formation followed by coupling. So we're pretty excited to show that in this case, what we think is happening, the carboxylic acids are coordinating to the catalyst surface such that you can induce the desired reaction. So that's how you're bringing your two substrates into the photothermal agent and engage it in productive chemistry. And so with that, hopefully I've shown you that we can use photothermal conversion for all sorts of manner of organic reactions, polymerization, depolymerization, and now even some intermolecular coupling reactions. So I just need to thank the group. It's a very new picture. I didn't highlight everybody's names, but hopefully I highlighted them throughout the talk. Great group of people to work with. They do everything. I'm very secondary to the process. Thank all of our funding sources, and thank you so much for the invitation and for all your attention. I'd be happy to take any questions. Oh, hi, Alex.
Hi, everybody.
You made it.
Yeah, thanks so much for a great talk, Erin. For everyone who's in attendance, if you have a question, there's a Q&A box at the bottom of the screen. If you could please input your questions there, and we will read them out. I guess in the meantime, Erin, I have a question, and I apologize if you address this, but with the depolymerization of the plastics, the products that you're getting out, like if you were to use this like as an industrial approach to, decompose plastics, would you isolate all of those different components and then reuse them? What's like the idea there with that?
Yeah, that's a great question. So one of the things you want to achieve in any sort of recycling process is to get a very clean product stream. Because isolations and separations, right, that's a whole nother ballgame in energy cost. And so what we've shown with polystyrene is based on boiling point, and this is how they do this in industry, they kind of separate things based on boiling point. And so you can get clean polystyrene to come off, collect it. Sometimes there's special purification things that it goes through. You can get pure styrene monomer, and then you can repolymerize it. What we've shown that we can collect the monomer and repolymerize it and get similar products. You know, in the case of sunlight, when we really only get styrene and a little bit of dimer and trimer, I think you could just repolymerize that and make more polystyrene. But my guess is industry would not like that, question of purity in that case, because you might get a few, side chains or something like that, which could change the properties a little bit. But yeah, but
Yeah,
that's
that
definitely
makes
one of the things we're trying to accomplish is get very good, very high yields of a single product so that you don't have to worry about separations.
Yeah, very nice. That the video you shared was really cool. How fast is that? Is that like a sped up video or
Yeah, it's a sped up video, but it is still
okay.
very fast. The sunlight experiment, I mean, it really only takes 3 minutes, and the polymer's gone. It's all monomer. With the LEDs, it's a lower intensity, and so it takes a little bit more. They're unfocused, broad spectrum LEDs. You can get them off of Amazon, and so there's definitely efficiencies we need to make up, but they're still pretty fast compared to getting out your sand bath and waiting for it to heat up and all that, right?
Yeah, very cool. Alex, you got a question?
I sure do. Aaron, really lovely talk. I very much enjoyed all of it. I missed, I think, only the first slide or two.
Okay.
So it seems really simple and practical. So question one, is there anything special we need to know about the charred catalyst or the carbon black if this were to be attempted to be used by somebody outside your laboratory?
Not really. We've looked at different carbon-containing materials, and so far we don't really see much of a difference. That's definitely something we want to look into, right? Especially when you're, this last part that I talked about, getting association between your catalyst and substrate. The surface chemistry is going to be really important. But if you're just trying to do, bulk heat transfer, especially intramolecular reactions, you just toss in any carbon black and it'll work.
Okay, so the bottle from Aldrich in the laboratory already
We
is
use it from Alpha, but yeah, yep.
okay. I'm sorry, what were you?
Oh, ours is from Alpha, but
Alpha. Okay, great. So regarding that last project, that the dimerization of the two different carboxylic acids,
Mhm.
is there any involvement of like a pre-organization of the two carboxylic acids that brings them together, like a temporary intramolecularity that's being taken advantage of?
Yeah, so the reaction is thought, so it's with all these different metal oxide catalysts, the reaction is thought to proceed through first absorption of the carboxylic acid to the surface, and then you get the coupling reaction. Now it's still unclear why we're getting such good cross-selectivity. But it makes sense that the aryl carboxylic acid can't couple with itself because you need to do that enolization. But it's not clear why the aliphatic acid is not coupling with itself, and you're getting sort of a statistical mixture. And so that we're still trying to investigate if there's just a stronger association of the aryl carboxylic acid to the manganese surface, catalyst surface, wow. Um, and what's sort of driving that product selectivity. So that's still under investigation, but it is thought that we have the two partners come together at the catalyst surface.
Okay, great. Really interesting. Thank you so much.
Mhm.
There is one question from the chat.
Sure.
Um, Rebecca asked, any ideas on how to apply this to destroying microplastics?
Yeah, that was one of our ideas with the porous carbon material. If you essentially filter the microplastics into the carbon, and then you could just irradiate it and then depolymerize the microplastics. And so I think that is a potential strategy. We pursued, more broad application to commercial plastics, but I think if you could just collect the microplastics in the porous structure, irradiate it, and then you could just get the monomers back. We haven't seen, I mean, we haven't looked at microplastics in particular, but we haven't really seen much of a size effect, particle size of the polymer in depolymerization. So I would imagine that microplastics would depolymerize just as well.
Thank you.
Mhm.
All right. If you could all join me in thanking Aaron one more time for a really great presentation. In keeping with time,
Get on
Alex,
time.
I'll turn it over to you to introduce our next speaker.
Great. Fantastic. Thank you, Alex. Okay, our next speaker for today's virtual symposium is Professor Mark Taylor from University of Toronto. Mark, it's a pleasure to meet you. I've never met you in person, so I'm looking forward to hearing about your science and having a small chat with you after this. Um, uh, Professor Taylor's background includes training at University of Toronto as an undergraduate, um, PhD work at Harvard, postdoctoral, a postdoctoral fellowship at MIT, and in 2007 he began his independent career back at University of Toronto. So a bit of a homecoming for Mark. And he's been at Toronto since moving through the ranks, assistant, associate, and now a full professor. Um, a few awards that Mark has received that I noted here include international awards as well as some local to his university, a Sloan Fellowship in 2012, a Keithani Award in 2017, and has recently been recognized by University of Toronto as a Dean's Research Excellence Awardee. So congratulations on all those very nice awards, Mark. I think the overlying theme of Mark's research will be methods development and catalysis. And that work spans a lot of different types of chemistry, including carbohydrate chemistry and many other unique applications of his group's studies. And with that, I think I'll turn the floor over. Mark, it's all yours.
Okay, thank you very much for the introduction, Alex. Great to meet you, and thanks for including me in this. Let's see, hopefully that is sharing. Hopefully that looks okay to everyone. So yeah, it's really a pleasure to be here today and to be able to share with you some of the work that my group has been doing. I'm going to focus on a project involving thinking about how to regioselectively functionalize amide and nitrogen nucleophiles, so azole type heterocycles. Before I do that, I would like to start by acknowledging the students who did the work. This is actually an older group photo, but I'm showing it because it includes really the two students who did all of the work that I'm going to be sharing with you today. So here we have Shrey Desai. He graduated with a PhD from my group a couple of years ago and is now a postdoc at NYU in the Parasaram group. So look out for Shrey. He's really a very talented young chemist. And the other key player in this work is Matthew Zambri, who just recently finished drafting his thesis and will defend later in the summer. This is really a project that went in a direction that I couldn't have anticipated, and so it's really to the credit of the students for taking in that direction. So I'll actually try to illustrate sort of how we ended up stumbling upon really this question of how to regioselectively functionalize nitrogen heterocycles. I'd also like to thank the students who the funding agencies, and in particular NSERC for really sustained funding of our research program over the years. All right, so as Alex mentioned in the introduction, we're involved in catalytic methodology development in a number of different areas, and for many years have been focused on the question of how to control site selectivity in reactions of organic molecules. And this started out as very much a hypothesis-driven project. We were hoping to take advantage of the molecular recognition chemistry of organoactive functionalizations, OH functionalizations of carbohydrates. And indeed, what we found is boron bonds and one BOH group will interact with cis groups in sugars to generate tetracoordinate adducts, which are then activated nucleophiles. So they'll react selectively with an electrophile at a rate higher than that of a free hydroxyl group, allowing for us to selectively monofunctionalize the carbohydrate and then turn over the organoboron catalyst. Over the years since making this discovery, we've been thinking about other ways to take advantage of these kinds of complexations to do selective chemistry on carbohydrates. So I highlight here an example of selective Chan-Lam type couplings where we use the boronic acid as both the aryl transfer reagent, but also as a transient protective group for the diol group in the sugar. So this allows us access to some interesting sugar-derived aryl ethers that would be difficult to synthesize by other means. More recently, we've been thinking about how to use these kinds of coordinations to activate CH bonds in sugars. And so this takes advantage of hydrogen atom transfer chemistry. So the diol adducts generated from the boronic acids have activated CH bonds. Those CH bonds are more hydridic than prior to the boron condensation. And so we can use this phenomenon to selectively generate radicals from sugars and then trap those to do homologations of the sugar backbone or redox adjustments. So while thinking about this chemistry of diols and organoboron compounds, we also got to thinking about what we might be able to do with epoxy alcohols as substrates. So you can imagine that ring opening of a 2,3 epoxy alcohol in the presence of an organoboron compound would generate a species similar to what we get from direct binding of a diol group to, for instance, a boronic acid. And so my student Kashif Tanvir showed that this was indeed the case. He was able to develop a number of interesting regioselective functionalizations of 2,3 epoxy alcohols, taking advantage of this kind of ring opening and then subsequent functionalization modes. So using, for instance, benzoyl chloride, he could accomplish a chloroacylation of the epoxy alcohol. We conduct a similar reaction in the presence of iodide. We get iodide-induced ring opening, followed then by a semipinnacle type rearrangement to expel the iodide. So iodide is co-catalytic in these reactions. Finally, if we move that hydroxyl group 1 carbon further away from the epoxide, we get a different type of mechanism here. We get sort of a temporary intramolecularity type mechanism where the boronic acid binds to the hydroxyl group and to the nucleophile, and then it delivers that bound nucleophile to the proximal position. So we get C3 selective ring opening of these 3,4 epoxy alcohols, which is often a challenging outcome to achieve. So it's here that the azoles come in thinking about alternative nucleophile classes that we might be able to explore for this chemistry. We became interested in 1,2,3 triazoles and other acidic NH azoles. They had similar pKa's to other nucleophiles that had been used successfully in this chemistry. And so Schrey was able to find that indeed this worked in practice. So you can see selective C3 selective ring opening of this 3,4 epoxy alcohol with 1,2,3 triazole. So this was sort of as we expected, but what surprised us here was the relatively high level of regioselectivity that we saw for functionalization of one of those two nitrogens. So of course, in 1,2,3 triazole, there are two possible regioisomers, N1 or N2 functionalization, and we saw very high levels of N1 selectivity. And this proved to be the case over a number of different ambident azole type nucleophiles, so including indazole, this triazolopyridine, purine, benzotriazole, substituted tetrazoles, etc. And so this was unexpected. We had anticipated that we would get mixtures of regioisomers in these kinds of reactions. And so Schrey turned to computational modeling to understand the basis for this selectivity. And what he found is that one's able to rationalize these selectivities by invoking a coordination between the organoboron catalyst and the pronucleophile. So again, similar to what I showed you for some of the preceding work. And if this coordination is selective, then the adjacent nitrogen is the one that's activated. So we get these 7-membered ring type cyclic transition states. And through this selective coordination and then activation of an adjacent nitrogen, we can account for the regioselectivity that we see in these types of processes. And so, and again, the utility of these compounds is they're somewhat reminiscent to acyclic nucleoside analogs that are quite an important class of drugs. But more broadly, we realized that this is quite an important general challenge in organic chemistry, this issue of how does one regioselectively functionalize ambident azoles. Some of the interest in this problem stems from the fact that, of course, azoles are very prominent scaffolds in medicinal chemistry. So I'm just showing you 3 of really hundreds of examples of such molecules that I could use to illustrate this. If we look at sort of wish lists from the pharmaceutical chemistry colleagues on reactions that they would hope would be developed, you'll often see this question of site-selective or regioselective functionalization of azoles being highlighted as a problem that's of sustained interest there. And so indeed, this is a problem that's really captured the interest of the synthetic community for some time, but in particular in recent years. So there are a number of really elegant strategies that have been advanced by the groups that I've listed below here. And again, this is not an exhaustive list. So the question to us became, is this sort of a one-off observation, this special case of 3,4-epoxy alcohols, or is there something more general that we can take advantage of here in using coordination of an organoboron catalyst to an azole as a way to achieve site-selective NH functionalization? And so, of course, to do this, we started to explore other classes of electrophiles. Enones were one of the first classes that we looked at, so trying to achieve aza-Michael type reactions. And I'm showing you here a catalyst optimization for analkylation of, again, this triazolopyridine pronucleophile. So what you can see is that using this ethanolamine ester of diphenylburinic acid, this is a very common precatalyst that we use. Diarylburinic acids are somewhat sensitive towards oxidation upon storage. One can protect them from that oxidation by generating tetracoordinate complexes. So this ethanolamine ester is a conveniently handled white solid that one can store in the fridge without issues. So when we use that precatalyst, we get relatively good yield and appreciable regioselectivity for the formation of the isomer that I'm showing you here. What surprised us is that if we then generated the free diarylburinic acid and subjected it to the same set of reaction conditions as this catalyst, we now see very low yield. So this really surprised us because, again, normally this ethanolamine is present just as sort of a spectator to stabilize that pre-catalyst. What we found is that by introducing another amine, so for instance, benzylamine, we could restore the reactivity of that diphenylburinic acid. So you can see now we're getting, again, appreciable yields of that inoculation product. So we think about this in terms of a mechanism involving activation of the enone as an iminium ion. And I'd say more broadly, what we found with this chemistry is that it tends to work best when the electrophile is a cation, so that we can benefit from an ion pairing interaction with this anionic tetracoordinate organoboron adduct. We carried out a number of mechanistic studies. I'm showing you here just some variable time normalization kinetic analysis that we did to show that it displays first order kinetics in the concentration of both of the co-catalysts here. So first order in diphenylburinic acid and first order in the benzylamine. So just a couple of examples of the types of substrates that we can use in these selective aza-Michael type reactions. You can again see 1,2,3-triazoles, purines, 1,2,4-triazole, benzotriazole, and in all cases, we're seeing relatively high levels of selectivity for one of the two or more nitrogens that could react in these kinds of systems. One feature of this that I'll point out here, and that's a general one in the context of this chemistry, is we often see these sort of contrasteric outcomes where the electrophile is introduced at what appears to be the more sterically hindered position of the heterocycle. So you can see here we're functionalizing adjacent to this hexyl or aryl substituent in these substituted 1,2,3 triazoles. So I'll get back to how we think about that in a moment. This mode of activation of the nucleophile is compatible with transition metal catalysis for activation of the electrophilic component. And so I'm showing you here palladium-boron co-catalyzed N-allylation reaction, where the palladium catalyst is serving to activate an allylic alcohol towards pi-allyl formation, and it's that pi-allyl-palladium electrophile that's capturing the boron complexed nucleophile to generate the carbon-nitrogen bond. So again, this is where Matthew came into the project, and so I'll show you a number of other contributions that he made over the course of the rest of the talk. So you can see here that this is a method that again applies to quite a broad collection of heterocyclic partners. Once again, you see these examples of contrasteric outcomes where we're functionalizing what appears to be the more hindered position. The method is tolerant of highly functionalized partners, so we can use some of these free NH tetrazoles that are used as drugs. We can carry out selective functionalizations of the NH groups in those kinds of compounds. This is also a useful method for activation of M and NO nucleophiles. So pyridones and related compounds present a regioselectivity challenge. It's quite an important one, I would say. And you can see that here we get selective N-allylation of a range of these types of partners. So that chemistry is outlined in this Sinlet paper that I'm citing at the bottom of the slide here. We're still, I would say, working to develop a full picture of what controls regioselectivity in these types of systems, but we have a basic computational model that often provides a useful starting point for how to think about this. And so what we're really considering in these calculations is the thermodynamic selectivity for binding of the boron to two or more of the possible nitrogens, along with the charge distribution in the resulting species. And so the charge distribution we're determining based on the Mulliken charges at each of those nitrogens. So you can see for a simple case like this pyrazole, there's two possible sites of coordination. Of course, the nitrogen that's not bound is the one that's going to react. And so if we look at this phenylpyrazole, the calculations predict that this should be the more stable, essentially boron tautomer of this azole. And indeed, we see selective reactivity at the position that's indicated here. Similarly for this tetrazole, again, two possible sites of binding. It's this adduct that's the more stable one, and we would predict this nitrogen to be the more reactive one. So again, this is an approximation. It ignores steric effects in the transition state as we functionalize that complex with an electrophile. So for instance, in this second example here, the steric effects are likely to further favor the complex that I'm showing you here because we're going to activate the less hindered nitrogen. We find, though, that this model does correctly predict the outcomes, or at least correspond to the outcomes that we see in some of these contrasteric cases. So here you can see this phenyltriazole case where we predict that the major adduct should be this one. It should selectively functionalize at the position adjacent to the aryl group. And similarly, these calculations give us the correct outcome in terms of this triazolopyridine adduct. Right, diving a little bit deeper into the mechanism of this cooperative organoboron palladium catalyzed N-allylation reaction, we thought this was quite an interesting reaction to study mechanistically because we have these two catalysts that are working synergistically. So if you really simplify the mechanism, you can think about it as involving two steps. There's the ionization part of the mechanism, more than two elementary steps, but we can think about it as being sort of one element of this mechanism. So the ionization step where we generate the pi allopalladium from the palladium coordinated allylic alcohol, and then the CN bond formation step where the organoboron complex nucleophile reacts with the pi allopalladium species. A word about this ionization step. This we think is assisted by the acidification of the azole that accompanies binding to the organoboron catalyst. So we calculate that the pKa drops by about 6 units upon coordination. And so then this acidic NH group can help us to dehydrate this complex to result in the pi allopalladium species. So if we think about substituent effects on the organoboron catalyst, in this first step, the ionization step, the organoboron catalyst is acting either as a Lewis acid, or perhaps you can think about it as acting as a Bronsted acid. So in either of those cases, we would expect electron withdrawing groups to speed up the ionization process. On the other hand, in the second step, we're destroying negative charge as this nucleophile undergoes N-allylation. So we should expect the opposite in terms of substituent effects on aryl groups here. So if we look at a Hammett plot for substituted aryl boronic acids as our co-catalyst, we see indeed that it has a positive slope. So that really points towards the ionization step as being turnover limiting in this process. We did a number of other mechanistic experiments and computational experiments that I won't get into, but I did want to briefly show you the kinetics of this reaction, which are somewhat unusual. So again, we use variable time normalization analysis to infer the rate law for this process. So I'm showing you here a plot that allows us to determine the kinetic order in the concentration of the palladium catalyst. So we run the reaction at 3 different palladium concentrations, normalize the time axis for the palladium concentration raised to the power of 1. The overlay of these plots shows us that we have first order kinetics in the palladium catalyst. That's useful information. You can get one other kind of information from this plot. So if you look at the concentrations of product versus time or normalized time axis, they're linear to relatively high levels of conversion. So linear product versus time plots are telling us that we have an overall zero order or apparent zero order rate law. So that's not impossible. I'd say somewhat unusual in catalysis, but this was obviously something that we took from this experiment as well. Nonetheless, we went on to determine the kinetic orders in the other species. So if we look at the order in the aryl boronic acid co-catalyst, we actually see apparent zero order kinetics in this species from concentrations ranging from 10 mole percent to 40 mole percent. So we're essentially saturating that organoboron catalyst through these concentrations. Zero order kinetics in the allylic alcohol component, again, consistent with overall zero order kinetics, but quite a surprising result when we look at the kinetic order in the triazole, in the nucleophile. Now we see first order kinetics in the triazole. So this is not what we expected. If the reaction shows apparent overall zero order kinetics, we can't have a kinetic order in one of the reagents. So we were quite taken aback by this and spent quite a bit of time thinking about what could cause such an observation and realized that what we were seeing here could result from an autocatalytic reaction. So if the reaction is accelerated by the product, then the effects of first order dependence on the starting material concentration could be compensated for by an accelerating effect of the product, giving what appears to be an overall zero order rate law. And so this is indeed what we see. If we add increasing amounts of this N-allyl triazole product to the reaction, we actually see an increase in the rate of the reaction. And if we analyze the kinetic order in the product, we see that we have first order kinetic dependence in that N-allyl triazole product. So again, the apparent zero order kinetics that we're seeing are arising because of the compensating effects of first order dependence on substrate concentration and product acceleration in the reactions. So as I showed you before, ionization is the turnover limiting step of this reaction. And so I'm showing you here a calculated transition state for that ionization, right? We're cleaving the carbon-oxygen bond to generate the pi-allyl palladium. And what we've been able to find is that this N-allyl triazole can act as a weak sigma donor ligand for this developing electron deficient palladium in that oxidative addition step, and so thereby stabilize that transition state in a way that gives rise to acceleration. So one question that we asked ourselves is, could we mimic this effect by additives that might be present from the outset of the reaction and that might be able to do this more effectively than N-allyl triazole? And so after quite extensive additive screening, Matthew was able to find this compound, trifluoroacetophenone, that actually serves to accelerate these reactions, presumably in a similar way to how our N-allyl triazole is acting by working as a sigma donor ligand. What's also important here is that it not be too Bronsted basic. If it's too Bronsted basic, it causes deprotonation of that acidic NH group that I showed you is important for the ionization. So there's sort of a sweet spot here where the additive has to act as a sigma donor but can't act as a strong Bronsted base. So in any case, you can see that by using this trifluoroacetophenone, we're able to reduce the catalyst loadings, the palladium loadings, in a number of these reactions. And you can see there's an appreciable effect on the yield of these reactions by the incorporation of this additive. So this is a pretty unusual additive in transition metal catalysis, and we're interested to see whether there are other situations where it might be helpful. Okay, switching to another class of electrophiles. If you think about modifications of NH azoles that are important in biology and in medicinal chemistry, glycosylation is really a crucial one. This is because these sorts of N-glycosides are nucleoside analogs, which are a tremendously important class of drugs, primarily antivirals and anti-cancer compounds, but also, of course, important building blocks for therapeutic nucleic acids, which are really a huge growing area of interest for therapeutics. It turns out that the N-glycosylation reactions that are needed to construct these compounds are actually quite challenging. So azoles are relatively poor nucleophiles, and on top of that are often quite poorly soluble in the nonpolar organic solvents that are typically used for glycosylation reactions. And so that means that these are not straightforward glycosylations to conduct. So I'm showing you here some examples of sort of state-of-the-art in glycosylations. For Bruggen-type glycosylations are a very important way to sort of pre-silylate the nucleobase in order to increase its solubility and activate it towards N-glycosylations. More recent developments along this line often take advantage of designer leaving groups. So you can see here the incorporation of this alkyne, which is activated by, in this case, a gold catalyst. So really gold catalysis under rigorously anhydrous conditions is, I'd say, the state of the art for accomplishing these kinds of transformations. So the hypothesis that we had was that, again, binding of the organoboron catalyst to the azole would acidify the NH so that it could be suitable for activation of a leaving group that's activated by Bronsted acid catalysis. And so these types of trichloroacetimidates and related imidate type leaving groups, which are very commonly used in carbohydrate chemistry, seem to us to be well suited for this purpose. So you can then imagine proton transfer followed by loss, in this case of trichloroacetamide, generating either the N-glycoside directly through SN2 type processes or an ion pair and then CN bond formation through an SN1 type mechanism. And again, there are a number of examples of organocatalysis using Bronsted acids to achieve these types of N-glycosylation reactions. So good precedent for this idea. You can see this ribosyl trichloroacetamidate being coupled here with a purine type glycosyl acceptor to generate the N-glycoside in quite good yield and reasonable, in this case, N9 to N7 regioselectivity. What I think is important to point out about these reactions is that they're quite simple operationally. So we're heating in toluene. We don't need any special drying agent. And these are reactions that are relatively insensitive to air and moisture, which is a contrast from several of the other N-glycosylation methods that have been reported previously. So I won't belabor the scope of this reaction overly. It's quite a useful way of generating 1,2-trans glycosides from these ester-protected ribofuranosyl type donors. So we can use this to install canonical nucleobases, but also to install unnatural nucleobases like triazoles, indazoles, etc. If we work with 2-deoxy systems, now we have a problem with stereoselectivity. So you can see that we get essentially equimolar amounts of the alpha and beta anomers here. And likewise, if our protected hydroxyl group isn't an ester type group, again, we tend to see alpha beta mixture. So there's areas here where we still need to improve in terms of stereoselectivity. Regioselectivity is usually quite high for these systems, again, as we generally see for these organoboron catalysts. Finally, this is actually a useful way to conduct N-glycosylations of these bioactive NH tetrazoles. So I'm showing you here one of these antihypertensive type drugs. So of course, the active form is the NH tetrazole, but we can glycosylate quite selectively using this method. Imagine that hydrolysis of this N-glycoside would release the active agent. One feature of this chemistry that we find quite interesting, and I'd say are still really struggling to understand, is that we can switch the regiochemical outcome of these reactions by our choice of organoboron catalyst. So typically the catalyst that we use for these reactions is this 3,5-bis trifluoromethyl phenylboronic acid. That, for instance, will deliver N1 functionalization of triazoles, benzotriazoles, etc. If we use this 3-pyridyl boronic acid, we actually get N2 selective functionalization. So you can see that's the case for benzotriazole and also for the 1,2,3 triazole shown here. You can also see changes in the regioselectivity for this indazole reaction partner. So while we don't have a full picture mechanistically of what's responsible for this switch, again, I showed you that acidic proton is likely quite important for glycosyl donor activation in these reactions. We suspect that the position of that acidic proton changes when we have this 3-pyridyl boronic acid, and that may cause a shift in the mechanism of these reactions. So in any case, this really highlights that there are opportunities to modify the structure of the boron catalyst in a way that influences the regioselectivity of these kinds of N-glycosylations. All right, just in the very last little bit of the talk, I'd like to show you some very recent work where we've tried to take a different approach towards this question of selective N functionalization of azoles, taking advantage of some relatively established concepts involving formation of hemiaminals from azoles. So I actually mentioned briefly this question of prodrugs for NH-azoles. One very well-precedented way to do this is to make these O-acylated hemiaminals. So this is an idea that was initially advanced by a group at BMS in the mid-1990s. You can see that this hemiaminal ester, when subjected to an esterase in vivo, is going to undergo ester hydrolysis. Then the hemiaminal breaks down to release the free NH tetrazole. And the advantage, of course, of the hemiaminal ester is that it's more bioavailable than the free NH tetrazole. These kinds of hemiaminal esters can be synthesized by a 3-component coupling of azole, aldehyde, and an acylating agent. Again, that's chemistry that goes back to the early 1990s. We were really sort of drawn to observations made by a group at Pfizer in 2016, where they showed that a hemiaminal sulfonate, so the species generated by trapping of this type of azole hemiaminal with tolsyl chloride, was able to undergo CC bond formation with organoaluminum reagents. So trimethyl and triphenyl aluminum allowed for the formation of the corresponding sort of benzylic tetrazole derivatives. And we thought that it would be interesting to try to explore, revisit essentially this bottom result in light of more modern discoveries involving deoxygenative type couplings. So the idea became basically, can we incorporate a redox active leaving group at this oxygen that would allow for radical formation to generate this azolyl methyl type radical, and then trap that, for instance, in a nickel catalyzed reaction to accomplish carbon-carbon bond formation. So the appeal in this method is that we would then be able to start with a combination of azole, aldehyde, and, for instance, a haloarine, and construct the 2 bonds shown here through this sequence of hemiaminal formation and then reductive coupling. And so indeed what we find is that using this mixed oxalate as our redox active ester, subjecting that to, again, nickel catalysis along with zinc as our reducing agent and a haloarine partner, we can give an electron to the oxalate. This fragments to generate the azolyl methyl radical. And again, that's trapped in the nickel catalyzed cycle, eventually enabling the aerylation of this compound. We can accomplish quite effective generation of the sorts of N-functionalized azoles that I'm showing you on the slide here. So really the nickel catalyzed reactions of these oxalate esters goes back to work that was conducted by Hegui Gong's group in 2019. So we're really taking advantage of that discovery and using it on these hemiaminal derived reaction partners. But you can see here that this is quite a general way to be able to construct the sorts of derivatives that I'm showing you here, particularly, I'd say, from NH tetrazoles and triazoles as our reaction partners. And so these are often substrates that are less well represented in other types of methodology that allow for construction of similar bonds. So we're quite excited both by the sort of modular nature of this reaction and more broadly about how we can use related hemiaminals as precursors for cross-coupling type reactions. So again, this is Matthew's work that was published just earlier this year. Okay, so that takes me to the end of the chemistry that I wanted to show you. So it just remains for me to, again, thank the students who conducted this work, thank the organizers of the symposium for including me. It's really been a pleasure to be able to show you some of our chemistry today. And of course, I'd be very happy to answer any questions.
Thank you, Mark. Okay, the floor is open for questions. And let's see. Okay, we do have a question from John, which I'll read to you. Let's see. It reads, in this 8, what other amine additives were screened? Any chance of an anti-selective variant with an azamichael addition?
Yes, it's a good question. Let's see here. So, sorry, I don't normally scroll through every slide, but don't know how to do it while sharing. Yeah, so the question is here, given that we're generating an iminium ion from the benzylamine, you might imagine that a chiral amine might allow us to do an enantioselective catalytic version. That's something we tried. We looked at it pretty extensively. Most recently, I had a fourth year undergrad thesis student who that was the goal of her work. We weren't able to find chiral amines that gave appreciable amounts of induction here. It seems that as you start to increase the steric bulk on the amine, the rates of the reaction tend to really fall off, and so that's a problem. But yeah, we did pretty extensive screening of primary amines to look for optimal reactivity, as well as chiral amines to look for enantioselectivity. In the end, that wasn't a very fruitful endeavor, I would say, although it does feel like it looks good on paper.
Okay, thank you, Mark. Any other questions? I certainly have 2, but I don't want to steal the floor if anyone else has one. Okay, Mark, you've touched on 2 things that I love very much, alylation chemistry and learning a bit more about glycosidic chemistry. So for the alylation chemistry, I saw that you were proposing that the alcohol is activated by a Bronsted acid, but did you consider a mechanism where it's like a condensation at the boron metal center? So you have both the heterocycle, the aryl and alcohol, and the allyl alcohol attached, and somehow that is driving the oxidative addition process.
No, you're absolutely right. And in fact, that's correct. In the end, the lowest energy calculated pathway that we can find has the boron coordinated to the oxygen of the allylic alcohol. And in fact, to
Okay.
rationalize our overall kinetics, we need for that to be the resting state of the catalyst. So yeah, overall, our catalyst resting state is palladium bound to allylic alcohol that's coordinated to boronic acid. That's what's consistent with the kinetic orders and also what calculation finds. Then there's a proton transfer that has to happen. The proton has to get from the nitrogen to the OH to allow for that to leave as BOH. I think I might actually have a slide on it if we have time. Let's see.
Do we have a few minutes?
Yeah, okay. So I go like yeah, so your instinct is a good one, Alex. So this is sort of exactly what we see. So right, the what we're proposing as the resting state is this species here, palladium bound to allylic alcohol bound to boron. Then azyl has to bind, and then essentially we get eventually to this transition state where, again, we've had to still protonate that oxygen to allow it to leave as BOH. So ultimately, that proton comes from the azyl essentially. But yes, this is the pathway that we're proposing for the ionization step.
Okay, cool. Thank you. All right, so one other question for you. On your glycoside chemistry, Is there a possibility of working this general synthetic strategy into C-glycoside formation? Like moving away from nitrogen nucleophiles?
Yeah, that's an interesting idea. I feel like yes. So our very first project, this entire boron catalysis area that we've worked in, it started out as a really simple project idea. It was trying to do direct aldol reactions of pyruvic acids, boron catalysts. So boron catalyzed because we had read a paper showing that boronic acids will stabilize the enol tautomer of pyruvic acids, basically. So that's how this all started. We realized that we were making tetracoordinate adducts and that those were the nucleophiles, and we sort of then took that into diols. But so there are a number of C-pro nucleophiles that are activated by making an boron compound or an organoboron complex. So you can use things like hydroxyketones, right? Pyruvic acids are another example. So I think that's what you need. You need a pronucleophile that is activated by, for instance, 2-point binding to boron, right? For instance, through 2 oxygens. I guess we've been kind of maybe intimidated a little bit by how good the methods using glycosyl radicals are, right? There's been just an explosion of research. Dawen Yu's group, Minju Ko, all those folks are just doing amazing stuff in that area. So it's been kind of hard for us to think about what we could do there that would really compete. But maybe phenolic C-glycosylations could also be a good fit. I probably haven't thought about that as closely as or as carefully as I ought to have. Again, in part just because of the intimidation factor from all the awesome radical stuff that's out there.
Thank you. Okay, I am not seeing any other questions, so let's please join me in thanking both of our speakers, Aaron and Mark. We really appreciate your time. Thank you for being with us, and all of our guests attending. Thank you for joining us this summer for a DOC virtual symposium. Thank you, everybody, and take care.
Thank you.
Aaron, good to see you. Mark, nice to meet you. I really enjoyed both of your talks.
Yeah, great to meet you, Alex.
Aaron,
Yeah, that was awesome.
Yeah.
Yeah, good seeing you, Alex. It's been too long.
Yeah, indeed.
Aaron, I'm particularly interested in your discovery of carbon black catalyzed SNAR reactions. We just discovered a new type of SNAR reaction, and we've hit a wall where it stopped working. And so now I'm curious if we just need to add some carbon black in there and it'll speed it up. I can't hear you. I'm not sure if your speaker's on or not, but I can lip read. Let me try again. No, don't worry about it. Okay, do we need to debrief about anything else, Alex?
I don't think so. I think we're
Okay.
good to
Oh,
go.
now.
Just
Oh, now
yeah.
it works.
Oh,
Yeah.
whoa.
Oh, yeah.
I was logged into my other televisit. That's why.
I see. Okay.
Log out, whatever. Yeah. I mean, maybe just adding a little bit of carbon black and giving it some light.
Yeah. In particular, I was asking about the dimerization of the two species, if that's important, because we know that our molecules come together and they're near each other,
Yeah.
but they don't do chemistry. So now I'm wondering if we can just locally heat them up next to some carbon black and
Yeah, if you know they're coming together, that's a great start. Because they
Yeah.
don't necessarily have to come into, they don't necessarily need to localize at the catalyst. Like we have another SNAR that we're working on as well, where it seems like they're coming together. And then, yeah.
Well, hopefully we're not working on the same SNAR.
Right? Oh, that's funny.
Oh, unrelated, but Mark, your student, Matt Zambri, is he
Yeah.
doing a postdoc or is he considering industry?
I think he'd think about it. Yeah.
Okay, but no plans as of yet?
No, I actually need to check back in with him.